Hi everybody, Dr. White here, continuing on with binomial random variables, and I promised to head back to our studio and do some more computational examples. So here's further example. This is based on exercise 7 in section 2.4. Suppose that 2,000 points are selected independently of each other and totally at random from a unit square. So it's as if you had a square, and I'm sorry, there's a slight typo here, and so I don't have time to fix it, but that should be a -1, and so this square goes from -1 to 1 on the x-axis, -1 to 1 on the y-axis. I'll show you a picture of it in just a minute. And let's let W be the number of those points that actually land inside the unit circle that's inside of that square, okay, out of the 2,000. So what we're looking at here is a binomial random variable, because every point that you pick in the square is like a trial. And the trial can result in success or failure. Success is if the point lies inside the circle, and failure is if it doesn't. So I'd like to find the probability of success. So for that, I need a picture of my situation. So here's my picture, x-axis, y-axis. And as you can see, x is allowed to vary from -1 to 1, okay? And y is allowed to vary from -1 to 1, okay? And so I get this square, which is so badly drawn that it looks not square, but it's a square. And then if you just graph x squared plus y squared equals 1, then you've got a circle whose center is the origin and whose radius is 1, so it touches the square at those 4 points that I'm trying to show. So if you're like throwing a dart randomly so that it could randomly land anywhere in the square, then you could figure intuitively the probability for the event that it lands inside the circle. It just seems intuitively that ought to be the area of the circle divided by the area of the square, since all points in the square are equally likely to be hit. Now the area of the circle is pi times the square of its radius, and the area of the square is its side, which is 2, total of 2, both sides squared. And so we get with pi over 4. That's the probability of success in this binomial random variable. Okay. So sorry about the typo right there. It should be a -1. So we got that W is binomial, 2,000 trials, chance of success pi over 4. So let's go ahead and compute its expected value. So that would be n times p, so 2,000 times pi over 4, 500 pi. Okay. Now the variance of W would be n times p times 1 minus p. So, I don't know why there's over 4s here. There shouldn't be. It's just n times p times 1 minus p. So that would be 2,000 times pi over 4, which is 500 pi. Then the 1 minus p is pi over 4. So sorry about those typos there. I'll take the over 4s out in the final version. The standard deviation is the square root of the variance, so square root of 500 pi times 1 minus pi over 4. All very great, well and good. Let's take a look at this new random variable z, which is W divided by 500. Okay, and I'd like to compute its expected value. So that's the expected value of W times 1 over 500, which is 1 over 500 times the expected value of W. So 1 over 500 times 500 pi. So it's pi. So I've got myself a random variable whose expected value is pi, okay? So if I try that random variable, then maybe I'll come out somewhere near pi. So let me try it once. To get our binomial, we're trying a random trial of this random variable. We're just going to do it once. And that random variable is, throw in 2,000 times at the dartboard with that chance of success. By the way, pi is how you get pi in R. And then, of course, divide by 500 to get the z. So this is a try of z. And we come out to 3.102, which is not a bad approximation to pi. It kind of stands to reason. If you have a chance pi over 4 each time, and you do it a lot of times, then the proportion of time should be about pi over 4. And so you could approximate pi by using your proportion. This z variable is a lot like a proportion. If you wanted to do it by throwing more darts, like say if you did 20,000 darts, then your random variable w, if you divide it by 5,000, would have an expected value of pi. And this trial here is based on a lot more dart throws, so I ought to be able to come closer to pi, and sure enough I do. I'm much closer to 3.1415 than I was before. So that's a kind of a nice application of a binomial random variable. Here's another one. Exercise 15 in the book. So say that a hospital obtains flu vaccines from 3 companies, Company A, Company B, and Company C. And 40% of its shipments of flu vaccine come from Company A, 50% of them come from Company B, and 10% come from Company C. And they've worked with these companies for a long time, and so say they've got enough data where they feel pretty sure that they know that 3% of the vials of flu vaccine from Company A are ineffective, 2% from B are duds, and 5% from C are duds. Okay. And the hospital gets a shipment, and you're not told like what company that shipment of vials is from, but it's some large number of vials. And the policy of the company is to test 5 vials from the shipment at random. And it's going to reject the shipment if 1 or more of the vials are ineffective. So suppose it rejects the shipment. What's the probability that that shipment came from Company C? Before you get any evidence about the shipment, you would say the chance the shipment came from Company C is 10%. But you've got evidence now. The evidence is that at least 1 of 5 vials you picked from that shipment was ineffective. Given that evidence, what's the chance that it came from Company C? So we're looking at a prior probability of 10%. We're trying to compute a posterior probability. We're in the Bayesian situation. So, we could trot out Bayes' theorem. The probability that it comes from C, given that we're rejecting it, is the probability that it comes from C times the probability that we reject something that would come from C, over this conditioning sum down here that gives you the probability of reject. And so let's just fill in what we know. The prior probability on C is 0.10. The prior probability on A is 0.40. The prior probability that it came from B is 0.50, and the prior probability that it came from C, again, is 0.10. We just need to get these other conditional probabilities, like what's the chance that you would reject a shipment that came from Company A, and so on. So let's think about this. let's let X be the number out of 5 that are bad vials. That's a bad word there. I'll change it. Let X be the number of vials out of the 5 you pick that are ineffective. Okay. Given that the shipment comes from company A, then X would be binomial with 5 trials, 1 for each vial having a 3% chance of being ineffective. If the shipment comes from company B, then X is also binomial, but with a different P. Same if the shipment comes from some company C, then it's binomial with the highest chance for ineffectivity on each of the 5 vials. So you could actually use that thinking to try to figure out what's the probability of rejection given that the 5 vials come from company A. I'll shorten that to PRA, probability of reject if from A. Now, that's the probability that at least 1 is ineffective. I'm going to think about that as 1 minus the probability that 0 are ineffective. So I'm asking for the probability that a binomial random variable is exactly 0, so I use d binom. 5 trials, chance of success 0.03 on each trial. Similarly, for the probability of rejecting if it comes from company B, I just changed the success probability. Same for C. So I compute those numbers, and then I head back to the Bayes formula and I put them in. So there was a probability of reject given C on the top, and here are the other conditional probabilities in their proper place in Bayes' theorem. And I'm getting about 0.18. So before we had evidence from the shipment, we would have figured there's a 10% chance the shipment is from company C. But now that we've got evidence of rejection, our estimate of the chances that it comes from company C has gone up, nearly doubled to 18%. So a nice application, not only of binomial random variables, but of Bayes' theorem. Let's try free throws again for another application. You're going to take some free throw shots. And let's say you have only a 10% chance to make each shot this time. What is the smallest number of shots you must take so that your chance of making at least 5 of those shots is at least 80%? That takes some thinking about to understand the question. So you can stop the screencast, just like read that for a while. And now let's have a go at it. One possibility is just to set yourself up a situation where you have that 10% chance of making each shot, but try a lot of different trials. Okay, let's try everything from 1 trial to 100. 1:100 is in R is actually 1, 2, 3, 4, 5, 6, 7, all the numbers up to 100. And so what I'm going to do here is I'm going to actually get binomial probabilities for each of those number of trials. There's a 4 here and a p binom. So what I'm asking for in this part right here is the probability of less than or equal to 4 successes when I'm doing my trials. 1 minus it would be equal to 5 or more successes. Probability of 5 or more successes. So this here is going to generate me a bunch of probabilities, 1 for every binomial random variable from 1 trial up to 100 trials, and what I'm computing each time is the probability of at least 5 baskets in that number of shots. So let's take this to our studio and head down to console. And I'm going to make this a little bigger so you can see it a bit better. I'm going to paste it in. And I'm going to run. Okay, and so I get a vector of 100 numbers, 100 probabilities, one for every number of trials from 1 to 100. You may have wondered, like, what are these little square bracket numbers when they print out vectors of numbers in R? It's telling you what place the row starts at. So like this first row, 1, 2, 3, 4, 5, 6 numbers, that is the 7th number in our list, and that's why they have a 7 right here. This is the 13th number in our list, and so on. Now remember, each of them is a probability. I want to see where is the probability, where for the first time does it get to be at least 0.8? And so I look and I see I'm a little bit below 0.8 right here, and I'm a little bit above 0.8 right here. So I'm at the very end of the row that had a 61. The next row starts at a 67, so that must be the 66th number in the list. The number of trials that generated that probability must have been 66 trials. So that's why I say, looks like 66 shots will do. That's the smallest number of shots I got to take so that me, as a lousy 10% shooter, has at least an 80% chance to make at least 5 shots. There you go. So that's it for binomial random variables. I'll fix the typos in these slides before you actually start working with them yourself. See you later.